This is a problem that we know two chemical reactions standard enthalpy change value. First one is ammonia reacting with oxygen producing nitrogen and water. The second one is nitrogen reacting with oxygen producing nitrogen dioxide. And we want to find out the standard enthalpy change of the reaction between nitrogen and water. And basically we have a target equation and we have two known equations. And known, we know its thermochemical value, and the target we want its thermochemical value. So this is, as we talked about in the class, a Hess law problem, where you manipulate the known equations to get the target equation, and then whatever changes that you made to the known equation you do to the delta H value to get the target equation's delta H value. Alright, so Hess law situations, we always label our known equations. We know 2, so 1 and 2. And we want the target equation, so 7 and 2 plus 12 water produce 8 ammonia, 6 nitrogen dioxide. And in Hess law problem, we examine our target equation and find out where is each component coming from, and then try to manipulate the known equations accordingly. Look at our first component of the target equation, nitrogen gas. And unfortunately, nitrogen shows up in both of the two target equations. That means, well, it's going to be hard to deal with it. How do you know its distribution into the two different equations? Whether it's, well, triple the first equation and using a single second equation, or double 3 or 1 and 5, you don't know. So in those situations, when the target equations component shows up in multiple known equations, we let it go. I'm not going to deal with you. I'm going to try to deal with the other components, and hopefully at the end of our calculation, this component is going to be taken care of itself. Alright, so next, water. Good. Water only shows up in equation number 1. So that means we need to manipulate equation number 1 to match the water in the target equation. Right now it doesn't match. Target equation 1, 12 water on the reactant side. The known equation 1 has 6 water on the product side. Okay, so we can change that. What if we reverse the known equation 1? Then we would have 2 and 2, 6 water produce 4 ammonia and 3 oxygen. It still doesn't match, but at least right now, after the reverse, water is on the reactant side. Okay? Now, remember, whatever you do to the equation, you've got to do to delta H. We reverse the equation, we got to reverse the sign of standard enthalpy change. Delta H is now positive 1314 kilojoules. Yeah. But of course, it's not a match yet. We need an exact match of 12 water molecules. Now we have 6. Well, we can always double the equation. 4 and 2, 12 water, 8 ammonia, 6 oxygen. Remember, if you double one component, you double every component. Otherwise, you would be losing your balance of the equation. Okay, whatever done to the equation, do the delta H. Double up, so double up your 13, 14, positive 26, 28 kilojoules. So water is all set. But still, this is not the equation that we want. We haven't used our known equation number 2 yet. Let's move on. Next component is ammonia. Well, what do you know? Ammonia is already taken care of. It only shows up in equation number 1, and we got it. Same side, same number. Good, no worries. The one after that is NO2. NO2 is only shown up in known equation number 2. Now, lucky for us, for known equation number 2, the NO2 is on the side that we wanted. It's on the product side. In the target equation, we want it on the product side as well. So there's no need to reverse anything. But the number doesn't match. Known equation we have 2. Target equation we want 6. That's easy to fix. We use known equation number 2. Let's triple it. 3 nitrogen, 6 oxygen, 6 NO2. And since we triple the equation, we're going to triple the delta H value, and now that's going to give us positive 206, 204 kilojoules. Now, so we manipulated both of our 2 known equations, and we looked at all our target equation components. And let's see if things are going to take care of itself for us here. We're going to add these 2 equations up. So 4 nitrogen, 3 nitrogen, 7 nitrogen. Oh, good. We want 7 nitrogen. 12 water. Alright, that's what we want to see as well. 6O2. We don't need that. Oh. On left, on right, we have 6O2. They cancel each other. Perfect. Then 8 ammonia and 6 nitrogen dioxide. Wow. That's our target equation. Dead on. Whatever you've done to the equation, do to your delta H. I added these two equations up. I'm going to add these 2 delta H up. And the final result is, of course, going to be 28, positive 28, 32 kilojoules. So the target equation would have a standard enthalpy change of 2,832 kilojoules if it happens according to the mole ratio in the balanced chemical equation.